In this video, we're going to talk about the ideal gas law. Ideal gases follow the molecular kinetic theory of gases. And in reality, real gases don't behave in that way. So, just as a reminder, there are, in this video, we are going to look at the ideal gas law. Here is a reminder of the different properties of ideal gases. So particles do not interact, which means there are no IMFs in gases. This isn't really true. However, we can make this assumption and still get a pretty good idea for the behavior of the gas. Also, the identity of the gas doesn't matter. So it can apply to any gas. When you have pressure, as a reminder, it is due to the gas molecules hitting the side of the walls of a container. So bigger containers have less pressure and less gas means lower pressures because you don't have as many gas particles to run into each other. Now, when you're looking at the temperature of a gas, you can think of it as the movement of the molecules. If you increase the temperature, then your molecules are going to move faster. So a higher temperature means that molecules are going to move faster. Like we saw with the ideal or with the combined gas law, there really isn't a time where you're only considering two properties of the gases. A lot of the times we have either all of the properties of the gases or in the combined gas law where we don't consider the amount. Now, the ideal gas law looks at all of the properties of the gases. So the equation for the ideal gas law is PV equals nRT. So this is the ideal gas law. We already know that pressure is P, V is volume, N is the amount, and T is temperature. The gas constant, which is given the symbol R, is equal to 0.0821 liters times atmospheres over moles times Kelvin. So the units of R tell us what the units of the different properties of our gas law have to be in. So pressure must be in atmospheres. Volume must be in liters. The amount has to be in moles. And finally, the temperature has to be in Kelvin. So if you get to a problem and your properties aren't in these units, you need to convert them into those units. Let's look at an example. If 10 grams of methane are added to a balloon at 295 Kelvin at 0.998 atmospheres, what is the volume of the balloon? The first thing I like to do is just write out my numbers and assign a variable to them. So the first number I have is 10 grams. That is an amount. So N is equal to 10 grams. If you recall, our N must be in moles. So I'm going to have to use the molar mass of methane in order to convert between grams and moles. So we can calculate the molar mass of CH4. And what do you all get? Yes, I get 16.05 as well. So I have to have grams on the bottom, and we can have mole on the top. So we can calculate how many grams we have. And I get 0.623 moles of methane. The next number I see is 295 Kelvin. I know Kelvin is a unit of temperature. My temperature must be in Kelvin, so I don't need to convert this. The next number I have is 0.998 atmospheres. Atmospheres is a unit of pressure, so that is my pressure. Also, for the ideal gas law, I have to have pressure in atmosphere, so that's great. I don't need to convert it. Finally, it says, what is the volume? So V is what I will be looking for. When I write out all of my units like this, it's very easy to see that I need to use the equation that has all four properties of my gases. And the only one that does that is the ideal gas law, or PVNRT, PV equals nRT. And I need to rearrange this to solve for volume. So volume is equal to nRT over P. Now we have that plug and chug situation. I can plug in my moles times R, and then my temperature. And I can divide that all by my pressure. Let me get a straighter line there, otherwise it's going to drive me crazy. Now notice that that did not make any difference. Oh well. Now notice our atmospheres cancel, Kelvin cancel, moles cancel, and I'm left with liters, which is good because I'm trying to solve for the volume. So go ahead and plug that out on your calculator. So we will take our moles, multiply it by the gas constant, and then finally multiply it by our temperature. You can get the answer of that. I get 15.09, and then we can divide that by our pressure. And I get 15.1 liters. So that is my final answer. When you're doing these types of problems, it's very important that you write out all of your numbers and assign a variable to them so that you can see what it is that you need to solve for, and then also determine which equation you're going to use. Let's look at another example of using the ideal gas law. Lead azide is a high explosive used in detonators. It decomposes to form lead and nitrogen gas. Determine how many moles of nitrogen gas have to be produced for the resulting pressure of nitrogen in a 100 milliliter container to be at 74.5 atmospheres at a temperature of 32 degrees Celsius. So again, I am going to write out all of my numbers and assign them variables. The first number I come across is 100 milliliters. So I know this has to be my volume. But if you recall, the volume for the ideal gas law must be in liters. So I'm going to have to convert this into liters. So that gives me 0.1 liter. The next number I have is 74.5 atmospheres. I know atmospheres is a unit of pressure. So that must be my pressure. Finally, I have 32 degrees Celsius. And I know that is a degree Celsius is a unit of temperature. Also get a clue from the problem because it tells me the temperature is 32 degrees. When you're using the gas constant, you have to have Kelvin. So I need to convert this to Kelvin. So I can take 32 and add it to 273, which gives me 305 Kelvin. And in this problem, I need to look for the question or bossy statement. So it is right here. Determine how many moles of nitrogen gas have to be produced. So that tells me my N is what we're trying to solve for. Here I have all four properties of the gases, so I know I have to use PV equals nRT. And in this case, I'm going to solve for the moles. So N is equal to PV over RT. And you guessed it, plug and chug situation. So I can plug my pressure in, 74.5 atmospheres, and multiply that by my volume, which is 0.1 liters. And then I can divide that by my gas constant, 0.0821 liters times atmospheres over moles times Kelvin. And then finally have my temperature. All right, go ahead and plug that in to your equation or into your calculator. So we can do 74 atmospheres times 0.1 liters, and then I can divide it by R and T. All right, what do you get? I get 0.298 moles of nitrogen.